The first and second derivative tests help us to find the extreme values based on the shape of the graph, but there are times that we are working on a restricted domain where that restriction creates a minimum or a maximum. Here's an example of this from single variable calculus. Notice that at the right endpoint we see the absolute maximum value for the function on the restricted domain, but that maximum is basically a construct of restricting the domain. If we extended the domain, the function looks like it would continue upward. There is a similar effect that happens in multivariable calculus. However, we need to be a bit more thoughtful. For a single variable function, the domain is a line segment, and the boundary is just the endpoints. For a function of two variables, the domain is a region in the plane, and the boundary is a curve, and we have to check the entire curve for extreme values. But before we do that, we will state the extreme value theorem, which also has a single variable calculus equivalent. Theorem: let f be a continuous function on a closed and bounded region R. Then f has an absolute maximum and an absolute minimum in R. This is an example of an existence theorem. Extreme points are guaranteed to exist for functions that meet these requirements. But the theorem does not tell us how to find the absolute maximum or minimum, nor does it say that the points that attain these values are unique. All it says is that such points are guaranteed to exist. The words closed and bounded refer to certain properties of the domain. Closed means that the limit points of sequences in the domain are also in the domain, and bounded just means the domain doesn't extend infinitely. We're not going to dwell on the technical details of these terms, but you should do your best to remember them for when you take a course in topology. The book provides a 4-step process for identifying the minimum and maximum of a function on a closed and bounded region. Step 1. Find all critical points in the interior. Step 2. Find all the critical points on the boundary. Step 3. Evaluate the function at all the points from the first 2 steps. Step 4. The minimum and maximum are the smallest and largest values from step 3. We're going to do example 10.7.8 from the book to demonstrate all of these steps. The full details of the calculations are in the book, so we're just going to focus on the big ideas. We want to find the extreme values of the function t of xy is equal to 2x squared plus y squared minus y, bounded by the equation x squared plus y squared is less than or equal to 1. Notice that the domain is a circle of radius 1 and its interior. The first step is to find the critical points of the interior. Setting the first derivatives equal to 0, we end up with the point 0, 1/2. Since this point is in the interior of the region, we need to include it. While we could use the second derivative test, it's not necessary since we're just going to evaluate and compare the values in step 3. That's a nice feature of finding extreme values on a closed and bounded region. For step 2, we need to parameterize the circle of radius 1. We know that we can use r of t is equal to cosine t sine t for t between 0 and 2 pi. So we plug this into the function capital T to turn this into a function of a single variable. And for this we can just use our single variable calculus skills. Taking the derivative and setting it equal to 0 gives us the equation cosine of t times negative 2 sine t minus 1 is equal to 0. Solving this gives us t equals pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. You may have to review some trigonometry for this, as it goes back to the concept of using reference angles and knowing in which quadrants the sine and cosine functions are either positive or negative. Strictly speaking, we should consider the endpoints where t is equal to 0 and t is equal to 2 pi. For this situation, extending the domain just means tracing the circle periodically, so this won't create any more potential extreme values. But if this were a rectangular region, those endpoints would be important. Now we're at step 3. We're going to calculate capital T at all the points we got from the previous steps. There was 1 point from step 1 and 4 points from step 2. Remember that little t gives us a coordinate by plugging it into the parametric equations, but we can also plug it into the single variable formula that we created. The last step is to identify the smallest and largest values and declare those to be the minimum and the maximum. The smallest value is negative 1/4, which happens at 0, 1/2. The largest value is 9/4, and it appears twice at plus or minus square root of 3 over 2, negative 1/2. This is one of the first truly multi-step problems of the course. As the problems get longer, it's important to remain organized in your presentation. This will help you to think more clearly and will help others to understand you better. There is no single right way to do this, but I recommend blocking off your work into steps. For step 4, I recommend writing your conclusion as a sentence rather than just putting a box around a number and writing a single word next to it. This may seem like a small thing, but communication is central to mathematics, and the sooner you learn to work and think in complete sentences, the better.